Okay, trying to convince you why this whole idea of conductivity is really essential, okay? And I think more fundamental than resistivity, okay? Because if you have resistivity in a situation more complex than a simple wire or a simple resistor, you're going to have to convert it to conductivity to make sense of it, I think. You won't have to, but it's one less conceptual step if you do that first. So what I'm saying is, now, first of all, if you're cranking a generator, you go back to this experience, right? Okay, if you got to crank harder, that means you got more current, because the current dissipates energy in a way that you're aware of. Okay, so you got to supply the energy, in addition to whatever it takes to overcome mechanical resistance, and there's inductance and stuff inside the coils and stuff like that. So it's like reactance and all that stuff that you have some concept of. Okay, but again, more mechanical resistance tells you that there's more current for a given cranking rate, which is a given voltage, because the cranking rate determines the voltage. And that implies less electrical resistance, right? So again, mechanical resistance and electrical resistance are completely different things, and one's reciprocal of the other. And the amount of current you get has a reciprocal relationship to the electrical resistance, the thing we want to call electrical resistance. And it makes perfect sense. This is resistance to current. You're applying a voltage. This thing is resisting your attempts to drive current. Okay? So if you've got a piece of nichrome, you're going to have easier cranking. Less mechanical resistance, but that's because you're getting less current and you have more resistance to the current. So that's the concept of resistance. It's a very simple concept. Now, we haven't started with the concept of resistance. We started with the concept of conductivity because it's deeper and more sophisticated to be able to reason things out by conductivity, okay? And something that y'all have been dealing with, since some of you come to me for, saying, okay, let's, I think it's this, let's try this, and some of you have written up some pretty good stuff, okay? But it's hard to pull all this together because there are a lot of relationships, okay? So I want to give you the advantage because I think you can pull it together. But anyhow, I keep saying, the way I conceive of conductivity is not by formula. Conductivity is what you multiply by the electric field in order to get the current density. Electric field and current density both being vectors. Okay? So if you have a situation with a wire, it really doesn't make a lot of difference if you talk about resistivity and resistance or conductivity and conductance, okay? But in a situation like this, where you have an electrode here, some kind of a fluid or whatever, some kind of material that conducts electricity, right? Allows you to drive charges from one point to the other. And you have these equal potential lines. And let's say this is at 1 volt, this is at 2 volts, this is at 3, 4, 5, 6 volts. Okay? So now my question is, and before we get to that, remember the potential difference, if you got a voltage between point A and B, and a distance between A and B, a VAB and an LAB, your electric field, just by reasoning out what the units mean, electric field being newtons per coulomb, potential difference being joules per coulomb, it's obvious that you would divide this by this to get the electric field. Because you divide joules by meters to get newtons. So joules per coulomb divided by distance gives you newtons per coulomb, right? Okay? Okay, well, just by that kind of reasoning, which can be real handy when you're sorting this out, you have this. Okay, so now at this point, we want to know what the electric field is. Now let me give you a hint. If you move along this curve, your potential doesn't change. How much work are you doing if you move along that curve? Well, potential is just the work you do per unit of charge, right? Or your potential difference, potential change. And since potential isn't changing, you're not doing any work. Now, if you're not doing any work, that means there's no force on the charge if you move in this direction. At least no force in this direction. Okay? Now, it follows pretty immediately, and I'm not going to belabor this because it's really something you get out of multivariable calculus. But this idea will help you when you take multivariable calculus. You'll have something to hang with all the stuff that you're doing on. Okay, it's going to be perpendicular to the potential line at every point. So you can easily draw the direction of the current. It goes here, and it stays perpendicular to this, and it's got to be perpendicular here, perpendicular here, perpendicular here, and it eventually goes back to the terminal. So there's a path that a charge might take. Now, it might go in this direction or this direction, depending whether it's a positive or negative charge, but it goes along this path. Well, you can now easily sketch a bunch of paths. Of course, the direct path here, if I draw these equipotentials, well, would be perpendicular straight across, right? And you go up here, you got to go like this and this and this and this. Okay? So you get this whole web of paths. Okay? Now my question is, what's your current density along this path? Or let's say between here and here. What's your current density along this path? Okay? Well, you know what your electric field is if you know the distance from here to here. Okay? Then you know what the electric field is along this path. Okay? Or at least in this vicinity. And you can multiply that by your conductivity to find out what the current density is at different points. So you get all these current densities. Now you can take a current density and multiply by the area of a little tiny circle perpendicular to the path, and I'm not drawing in 3 dimensions, but you get the idea, and get the flux of the current through that little circle, okay? So those are ideas you really kind of want to think about to give you an idea of why conductivity is an important concept. And if you're thinking in terms of resistivity, then you got to think reciprocals. It's easier to think of straight multiples and not have to keep reminding yourself, it's got to be reciprocal of that thing, okay? Because when you dive into this, your intuition can get away from you a little bit, okay? So you just got symbols and you multiply instead of dividing, and pretty soon you create a nuclear explosion in your water or something like that. I don't know. Yeah.
What's the difference between resistance and resistivity?
You should figure that out, but I'm going to do it for you here. Okay? That's kind of where we're leading. Okay? So, let's do that.